All right. Okay, Khadija, let's start with the class then. Already 15 minutes have gone. Other students haven't joined. Okay, only you have joined. They are lost, and I'll not wait much because already 15 minutes have gone. These lessons I won't be repeating in the class. See, latent heat is what amount of heat required to change the unit mass of substance completely from one state to another. See, in the previous cases, we had seen that there was a change in temperature in specific heat capacity, right? Delta T we were using, T1 minus T2, T2 minus T1 we were using. But if one state changes, understood? If the state changes, then we call it as latent heat. So very easy formula, Q is equal to mass into latent heat. This is the formula, very easy formula. M is the mass, L is the latent heat. Okay. Now, how is the change of state occurring? Look, changes of state occurs like this. Initially, you have minus 10 degree of ice. You provide heat to it. So suddenly it does not become water. First, the temperature changes. And when temperature changes, we use the formula MC delta T. All right. Then it becomes 0 degree ice. Then you provide further heat. Now the temperature remains constant and from ice it becomes water. So see, temperature is not changing, only the material is changing, only the state is changing. So here you will use the formula ML. Then see, again you have provided heat. Now water will remain water, but 0 degrees Celsius heat will be changed to 100 degrees Celsius. So this we will use the formula MC delta T. Then 100 degrees Celsius water to 100 degrees Celsius steam. So temperature is not changing, only state is changing. So MLU will use. Understood? Very easy. You just see whenever temperature is changing, you use MC delta T. Understood? Whenever you will see temperature is changing, you will use the formula MC delta T like this. Okay, whenever you see this. And if you see state is changing, ice to water, water to steam, use latent heat. In those cases only latent heat is. What are the processes that are occurring? These names can be mentioned to you. That's why I have written this. If solid is converted into liquid, we say melting. If liquid is converted into solid, we use the term freezing. If liquid is converted into vapor, vaporization is used. If vapor is turned into liquid, we use the term condensation. You must have heard of condensation of clouds. Then, if solid directly changes into vapor without passing through liquid or anything, we call it as sublimation, and opposite of it, when vapor directly changes to solid without any interference of any other state, we call it as anti-sublimation, solidification, or deposition. These terms, this is not easy, this is not very important. This won't come separately to write as a definition. But in the questions of latent heat, it can be mentioned. So that's why I'm telling. All right. So during the state change, just remember that during the state change, heat energy is used to change the heat energy is used in changing interatomic separation, no change in temperature. So latent heat are also of different types. You have latent heat of fusion, you have latent heat of vaporization. So nothing else. In the formula, it will be the same, L only. Here also, ML. But what is meant by this? Fusion means from solid into liquid. So we use the term latent heat of fusion. Latent heat of vaporization means from mass of a liquid into gaseous state. That is latent heat of vaporization, like this. If it is sublimation, if I give you a third part, like sublimation. So what will sublimation be? Okay, again, you will use delta Q is equal to M, LS. Whichever is mentioned, use that. And if formula of L is asked, latent heat, that is charge, the heat per unit mass. This is the heat. So SI unit will be joules. This is the mass. So SI unit will be kg. So total SI unit becomes joules per kg. And if you write this in CGS, this becomes calorie per gram. This becomes calorie per gram. So what have we discussed? Latent heat is when one state is completely changed into another. States of matter. You know there are three states. Solids are present, liquid states are present, gaseous states are present. So if any of these are changed into any of these without the change in temperature, temperature has to be constant over here. We call this as the latent heat. Tell me one thing, Khadija. Is it clear to you? Do you want to ask anything? Write it down. Anything you want to ask, you can ask. And keep on updating me in the chat column so I can scroll accordingly. Okay, then, Khadija, coming to questions. This says that calculate the heat required to melt 10 kg of ice, and latent heat of fusion is already given. So where you have to calculate the heat. So delta Q will be M into LF fusion. Mass is 10 kg. What is LF? Latent heat of fusion given 3.3 into 10 to the power 5. So answer will be 3.3 into 10 to the power 6 joules of heat. Likewise, you have the question, calculate the heat required to vaporize 100 kg of ice. All right, vaporize 100 kg. All right, if you have to vaporize 100, if you have to vaporize 100 kg of water, this is saying you have to vaporize 100 kg of water. Again, the same thing, delta Q is equal to M into LV. Mass is 100 kg. Latent heat of vaporization is 22.6 into 10 to the power 5. So which is 22.6 into 10 to the power 7, like this. And see, if we plot the graph of all this will look like this. Initially, minus 10 degree of ice there is a rise in the temperature, 0 degree ice. Then there is no change in heat, there is a change in state. Then there's a big change in temperature from 0 degree Celsius to 100 degree. Then now temperature remains constant, so water changes to steam. So in the first case, we use MC delta T, second case, we use MLF, third case, we use MC delta T, fourth case, we use MLP, like this. Okay, write it down. Okay, next question says that calculate the heat required to convert 3 kg of ice. Now, the same thing which I have told you, the formulas that you will be using, it's just that now we'll be applying them. How the questions come. So see, here again the same story is built. Ice is given and now the temperature is given -12 degree. So first from -12 to 0, 0 to 0 degree water, then 0 degree water to 100 degree water, 100 degree water to 100 degree steam. This entire is given and all everything. Specific heat, then specific heat of water, latent heat of fusion, latent heat of steam, that is vaporization. Everything is mentioned. So in the first process, how will we write the answer? Total heat will be, see, first heat is there, Q1, plus there will be a change in heat here, Q2, delta Q1, delta Q2, plus change in heat, delta Q3, finally change in heat, Q4. In first one, state is remaining the same, temperature is changing. So it will be MC delta T. All right. This will be MC delta T over here. So how will we write the answer? Final answer, how will we write? Delta Q will be M, mass. Let me write the mass as it is. C also I'm writing as it is. Change in temperature. It's 0 degree minus, this is -12. MC delta T plus. In second one, temperature is remaining constant, but state is changing. That is latent heat of fusion. Third one, again MC delta T, because 0 degree water to 100 degree Celsius water. Here we use MC delta T. Whenever you see temperature is changing, it's directly MC delta T. So temperature changes 100 minus 0. Last one is M into latent heat of vaporization, because from water it's getting converted into steam. One thing we can do common, mass we can take common. What are we left with? 12C plus latent heat of fusion plus 100C latent heat of vaporization. Okay. This is specific heat of ice. This is specific heat of water. This is, now you just have to put in the data. How much mass was started with? 3 kg. So 3 kgs. 12 into specific heat of ice, 2100, plus LF, latent heat of fusion, 3.35 into 10 to the power 5. So 3.35 into 10 to the power 5, plus 100 into specific heat of water, 4186 into 4186, plus finally latent heat of vaporization, steam, 2.25 into 10 to the power 6. 2.25 into 10 to the power 6. So finally, you should solve all this. You will see the final answer will come around 9.08 into 10 to the power 6 joules. This is how we apply. Now tell me, is this question clear? Similar to what we were studying? Clear, Khadija? Yes or no? Okay, okay, very good. Write it down. I think question also you haven't written. Write down the question. Just calculate heat required to convert 3 kg of ice at -12. And this is 100 degrees Celsius steam. Here, this is steam. Okay, now the next topic, that is calorimetry. So basically, calorimetry is a technique which we use to measure heat exchange. There's just one law of calorimetry. There's a device known as calorimeter. This is constructed in this manner, that two concentric vessels are taken. One is this copper vessel. Outwards, we cover it through a wooden jacket. All right, this is completely made up of wooden jacket. Why? To provide insulation. Copper is a good conductor, right? Wooden jacket is not a good conductor. It's an insulator. That's why to insulate the system, we keep a copper wooden jacket. Inside this is a metal conductor copper vessel. We put a thermometer here and a stirrer. Whatever contents we are mixing, to mix that we have stirrer, and to measure the temperature we have thermometer. One principle is that law of heat exchange, that is heat will be conserved. Mainly this means that heat will be conserved in the sense that heat lost will be equal to heat gain. This is the entire mechanics behind it. This will be cleared through the help of this question. You see, through the help of this question, you will be able to understand how to apply heat gain is equal to heat lost. See, the question says a sphere of aluminium of 0.047 kg is placed for sufficient time in a vessel containing boiling water so that sphere is at 100 degrees Celsius. It is then transferred to 0.14 kg copper calorimeter containing 0.25 kgs of water at 20 degrees Celsius. Then temperature of water rises and attains a steady state at 23 degrees Celsius. You have to calculate the specific heat of aluminium. Basically, what is happening initially is this case. This is the initial case. This is filled completely. The vessel, the copper vessel is filled completely. Aluminium is present outside, which is having temperature 100 degree Celsius. All right. This is copper. Then finally, what is happening? This is, I'm taking the same copper material only. Within this water, this aluminium has been inserted within, all right, in water. And this is the final situation. This is what is the question saying. So how will you summarize this? How will you answer this? Basically, you will apply the heat concept. Whatever is the heat lost by aluminium, this is equal to heat gained by the water. Water, and not only the water, the container also, that is the copper vessel. Do you get it? This is only what you have to use. And this is the entire theory behind this calorimeter. How will you write? Heat lost by aluminium. It will be MC delta T of aluminium. Everything will be of aluminium. Is equal to heat gained by water. How will you write it? MC delta T for water. For water plus MC delta T for copper. That's it. That's what you have to write. Understood? Have you understood this? Then only I'll substitute the values. If you want me to repeat anything, just let me know, Khadija. Then only I'll put the values. Clear? Okay, it's fine. Okay, good. Now see, mass is given as 0.47 into, this is unknown, this you have to calculate. This was the question. Change in temperature from 23 to 100. Again, mass of water is given as 0.14 into, this is also given specific heat 0.386, and change in temperature is 23 minus 20. That was given, no, 20 for water. Plus mass of this copper is 0.25 specific heat 0.25. Okay, total is 0.25. Specific heat of aluminium is asked. And for copper, it's not given. Sphere of aluminium, this much is placed in sufficient time containing boiling water. So this is 100. It is then transferred to 0.14 kg calorimeter containing 0.25. Okay, now copper we are putting it for water. Right. This data was for copper. Just exchange it. This data was for copper. This was already mentioned. So here I'll put MC for water. We know it's 4200. That's why it was not mentioned. So whenever you will perform the calculation, this final answer for this will come out to be 0.911 joules per kg per Kelvin. This you can solve, cross-check. And if you won't get the same answer, you can update me and let me know. Write this down. Wherever you get stuck, ask me. Khadija, if you've completed, you can leave. This completes latent heat part. Then we'll start with thermal conductivity on Tuesday. Okay.